Okay, so as James said, this is about multiple inheritance hazards, but specifically independently typed algebraic hierarchies. And so specifically, we're looking at how choices of how multiple inheritance is implemented for structures, so structures that inherit multiple other structures, interacts badly with dependent types. And we're going to explore this by looking at algebraic hierarchies, as these are a natural place where these problems arise. I'm going to be using lean code samples for the rest of this talk, but it's not just about lean. You can reproduce these as using Calc2, and until a recent version of lean 4, you could reproduce it there as well. The examples won't reproduce in non-dependently typed languages. So let's start by motivating algebraic structure. We might have a proof that addition on the rational numbers is commutative, and probably we also know that addition on the integers and the real numbers is also commutative. But we really don't want to give all these things different names and repeat them over and over again, especially because then all the downstream results have to be repeated too. This is not a remotely new problem. It's algebraic structures. Lean solves this via type classes. Calc does it via canonical structures. Isabelle has locales, and I'm sure there are other solutions in other systems. The majority of this talk is about type classes, but I'll sketch the analogy for canonical structures at the end. Of course, in this example, we don't really need a ring to show that addition is commutative. We could have a much more general algebraic structure. And we can take this generality to an extreme. And so this is a small graph of the algebraic structures in MATLAB. And so at the top of this subgraph of all of them, we have field, and near the bottom we have the plane operators, and somewhere in the middle are monoids, semi-rings, commutative monoids, groups, that type of thing. And this should make it clear the motivation for multiple inheritance, because almost every node in this graph has two nodes below it, so every structure implies more than one weaker structure. This graph is way too big for this talk. For the purpose of what I want to show, we only really need a very small subgraph. So we're going to look at these 6 nodes. Zooming in on these, they are a grid made of 6 nodes. Ring is the kind of strongest type class, and additive monoids are the weakest, and in between we're removing things like commutativity or negation. There's one more thing we're removing multiplication from the top row to the middle row. And so if you look at the top left, the arrows at a ring indicate that a ring is a semi-ring, and every ring is also an additive commutative group. This encodes naturally in the type class system of lean. We can replace each one of these nodes with a lean type class. So for instance, ring, which extended semi-ring and additive commutative group, now just use the extends keyword to say it extends these two things. Going in the other direction, at the very bottom of the hierarchy, we say additive monoids have a 0 and they have an addition. Add groups take those and add negation, and semi-rings take those and add both 1 and mul. And these fields are propagated backwards through the arrows. So as a result, ring should have a 1, a mul, a negation, a 0, and an addition. And obviously, these should be algebraic structures, so we should have some proof fields in there, such as addition being commutative or associative and that type of thing. But that's really irrelevant for the context of this talk. And in fact, the other fields are irrelevant too, but they sort of help to see what's going on. This extends keyword isn't part of the type theory. So lean just has a rule for when it sees extends, it's going to translate it to something else that's more fundamental that is part of the type theory. And strictly speaking, structures aren't in the calculus of inductive constructors either, but you can just view them as one constructor inductive types. So we'll pretend they are. So this isn't supposed to be a talk about lean, so we're not going to use this extends keywords. We're going to look at 2 things that it could mean. So the naive thing it could mean is when you see extends, you take everything in the list of things you extend, and you just turn it into a field of the class. So ring here would be a class with 2 fields, one of which is the semi-ring, and one of which is an additive commutative group. And the 2 bottom lines are nonsense to tell lean how to find those pieces. But this is a really bad idea because now you have 2 additions. You have one addition that comes from the semi-ring and one addition that comes from the additive commutative group, and either they're different, in which case this isn't a ring at all, or they're the same, but you've now got to add a proof that they're the same, and this just gets worse and worse the deeper your hierarchy goes. So you definitely don't want to do this. So the actual 2 options I'm going to compare, one of them is flat, where you take every field that is in all of the transitive closure of the dependents, and you just paste those into the ring class. So ring just has all 5 fields listed out manually. The other thing you can do is a slightly more clever version of the naive scheme I just showed, where you go through the list, and if none of the fields in the item you're at overlap with the ones you have so far, you add that field directly. So here, we start with no fields. We look at semi-ring. That has no intersection with the fields we already have, so we can just put 2 semi-ring in directly. When we get to add from group, we can't do this because the add field overlaps. So instead, we just add the fields that don't overlap. So here we add negation. Then, once we've done that, we need to show that rings imply semirings and rings imply additive commutative groups. And I'll explain this more on the next slide. So, if we think about the representation internally of the flat inheritance, we have this ring structure, which is the outer box, and it has these 5 pieces inside that are all at the same level. And I'm drawing these in one color to sort of show they're all the same term. Whereas in the nested case, you have this ring on the outer level and the negation fields on the outer level, but then the adcom monoid is somewhere in the middle, and it kind of nests down to additive monoids at the top. And so this thing is very asymmetric. And that sort of reflects in how the code you're writing for these two is longer for the nested. But this isn't about code length, this is about an actual problem that you run into when you do this. So the thing to realize here is this is looking at the first instance. So ring to semiring on a flat is taking apart all the pieces and putting them in a new box, which is like the new outer application of the function semiring make. Whereas for the nested case, we don't need to make a new wrapper at all. When we go from ring to semiring, we're directly projecting from a field. So we're really just zooming in on this single term to a piece in the middle of it. However, if we look at the other inheritance path, so instead of ring to semiring, we look at ring to additive commutative groups, then we have a different picture. So the flat situation is exactly the same, take apart the pieces, put them back together. So flat's always easy, you always know what's going to happen. For the nested case, because additive commutative groups weren't one of the fields of ring, we now have to do the same thing. So we have to take apart the ring, we have to take apart the additive commutative monoid, and only the little piece in the middle are we able to reuse. So we can reuse this zero and add term, but we can't reuse everything else, and we have to build a new wrapper. And we're going to call these paths that take everything apart and put them back together again non-preferred, and the ones that are just zooming in on a little piece preferred. And we'll see why in a moment. So every class must have one preferred parent. You could construct hierarchies where you have more than one preferred, but for the one that we're looking at, you have to have exactly one preferred parent. There are many ways to arrange the arrows in the diagram I showed in the first slide. Why is this diagram not showing? That is unfortunate. Okay, I will hope that will appear somewhere else. So, flat inheritance and nested inheritance. Flat inheritance is what Lean3 used. At least it used with this option that all of MATLAB set. So essentially, while Lean3 supported a very bad version of nested inheritance, nothing used it, so it didn't matter. It has no Lean4 support. Nested inheritance had, as I say, incomplete support in Lean3, but now it has full Lean4 support. And the other thing of interest here is that COC has flat structures by default. Sorry, COC, I said that wrong. Hierarchy Builder is generating structures, and the heuristic it's using to generate them is producing these flat structures and not the nested structures. So really this problem, we're only really seeing this problem in Lean4. Everything else has avoided it by some way or another. The problem that I'm going to get to eventually. So does the difference matter between these two? And the answer is yes. And the way we found this out was by porting a million lines of MATLAB code from Lean3 to Lean4 and finding out that things that used to work in Lean3 stopped working in Lean4 and tracked it back to the difference between these structures. So to see the case where the choice of flat or nested matters, and indeed where it first caused a problem for MATLAB 4, we need a type class which itself consumes type classes as parameters. So here we have the module type class, which provides scalar multiplication, or small, and ensures it's compatible with the multiplication and addition. To even state these compatibility requirements, we need a semiring instance to provide the operators which I've highlighted in blue, and an additive commutative monoid instance to provide the operators I've highlighted in red. This pattern is very common in Lean's MATLAB. Some other examples are algebras over a ring, or C-star rings from functional analysis, which kind of nest this pattern twice. So we have C-star rings taking a non-unital ring, star rings taking a non-unital semi-ring, and C-star rings taking a star ring. So if we can fix this, if this problem appears in one place, it's going to appear in a lot of places. For the purpose of this talk, we only care about the module type class. And indeed, we don't care about any of the parameters. We only care of the proof fields. We only really care about this single small data field. When we have a type class, there are two orthogonal next steps that are obvious to take. The first is providing some instance of the type class, such as stating that multiplication on a semi-ring can be viewed as a scalar multiplication, turning it into a module. So we just set the small field to multiplication. The second is writing lemmas that consume the type class we defined, such as the fact that negation commutes for scalar multiplication. A natural hope would be that we can now apply this lemma to the instance we just defined. So here we're saying, If we're using this scalar action defined in terms of multiplication on negation, then we can still distribute that negation over it, and we would just directly call the lemma. With flat inheritance, this works fine. With nested inheritance, we get stuck. We get an error saying it can't find a modulo RR instance. We can try and help it a bit, so we can tell Lean with a have I, look, here's exactly where this modulo RR instance is, please solve the problem. And the error message now says, yes, I have modulo RR, but where's modulo RR? So something's going wrong here. And this isn't a type class issue. There are actually extra pieces of data in this module type. So when we defined it, we had the first two arguments, which were R and M, but then there were the two arguments outlined in blue and red, the semiring and the encode monoid, and we haven't looked at those values. So I've expanded it here, and if we then show what those values are, what's important here is at the bottom of the slide, we can see that inst, the instance we created to try and help Lean, has different parameters to the one that it's looking for. And the question becomes, how different are these values? Does Lean consider them equal, or does Lean consider them not equal? And so to summarize here, the instance was built with, had this IS parameter, and it was populated by converting a ring to a semiring. And the lemma had both an IR and an IG parameter, and the IG was populated by converting the ring to an outcome group. And so what we end up doing is comparing these two, and we can see that the two blue paths clearly match, so we found the same conversion from rings to semirings, but we found two different conversions to go from a ring to an additive commutative monoid. And so what sort of happened here is our choice of lemma has steered the path that type class search has chosen to get from the strong type class to the weak type class. So this is, the semiring terms are definitely equal. Are these terms equal? We can ask Lean that, so we write out the first one, we say it's equal to the second one, and we write refl, which says which is the proof for things which are equal by definition. And with flat inheritance, everything is fine. And with nested inheritance, we get the same error we got before, saying this doesn't work as a type error. And this happens in COC too. This is not just a Lean problem. You would have to reproduce this identically, you would have to write some type classes in COC, which I know isn't the idiomatic way to do things. I will get to the packed structures version eventually. So what's going on with flat structures? So with flat structures, the paths on our sub-hierarchy of 6 nodes, we're going to zoom on the top 4, and they're all dotted lines because all of them take things apart and put them back together again. And the path around the top and down the right is this semi-ring to adcom monoid, and the path down the left and across the bottom is the adcom group to adcom monoid. And we can kind of visualize what's happening along these two paths. So in both cases, every time we go along an arrow, we take apart all the pieces and we put them back together. And the question we're left with at the end is, are these two things definitionally equal? And they are obviously definitionally equal because they're applicating the same functions to the same arguments. We can repeat this for nested structures. When we do it on nested structures, we now have these two preferred paths, the solid arrows. So the ones from the top are preferred, and top right are preferred, bottom left are non-preferred. And so the preferred path is simply zooming in twice. But the non-preferred path is doing this unpacking and repacking step. And so now we're looking at equality of these things at the bottom, and while these are still provably equal, they're not equal by definition anymore. The question might be, why are these not true by definition anymore? And so really we have this term IACM, which is an adcom monoid, and we're trying to ask, is this definitionally equal to making a new thing out of the single field inside it? And the problem we were looking at the previous slide with this diamond not commuting would initially make you think of this competing inheritance paths paper, but this was about making the data fields all compatible with each other. And in this particular example, the data fields are already all compatible with each other, and yet still we're finding that our diamond doesn't commute. So the answer here is to change the underlying type theory. So if you change your type theory such that you consider these things equal by definition, then the problem goes away. And so, as a simple example of where this comes up, if you define some point type that contains an x field and contains a y field, and you say, is the point equal to taking the point apart and putting it back together again, by definition, in Lean 3 this was false, and in Lean 4 it was true. But it was only true sometimes, and it turns out it was not true during type class search, which was exactly the place that we needed it to be true. Some other places where this comes up, which are just convenient, you can have nice equalities like the inverse of an equivalence is the original thing by definition. And there was some complicated diamond that was of the form of the previous paper. relating to subalgebras over themselves that couldn't be fixed without this change to the type theory. But what we really care about is this type loss case. So this is called eta reduction, or maybe just eta for structures. There's people in the Lean community have been calling it eta reduction, but it's arguably not really reduction, because it's just a rule for when things are definitionally equal. In terms of language support, Coq has this disabled by default, but you can turn it on. But because hierarchy builder, which is what MathComp uses flat inheritance, it doesn't really matter because the problem only appears when you're using the nested inheritance. Agda has it on by default. You can turn it off, but I think they foresaw that it would just be nice to have for convenience reasons, and then didn't run into any of the problems that would have happened if they hadn't turned it on. Lean 3 didn't have it, but didn't use nested inheritance, so it didn't matter too much. Lean 4 had it, but it was disabled during type class search, which was unfortunate. There was a transition phase when we were converting from MATLAB 3 to MATLAB 4, where we were completely stuck and we couldn't make any progress, and before committing to whether this was a good idea, there was a flag you could turn on temporarily, much like primitive projections and no eta equality, but only for the context of instant synthesis. And a few months later, finally it was merged into Lean 4 and we had this globally, and we were able to port the rest of MATLAB. But let's imagine we're stuck in a type theory where we don't have this eta for structures. What can we do? One thing you can do is just use flat inheritance, which is what Coq did. But if you don't, I seem to be having major problems with my diagrams. Let me refresh my window. It's forcing these nested structures upon us, and we have to insert some preferred digit somewhere. So what we can do is we can just make this dummy type class that sits right at, so this is the path that didn't commute. We can stick this dummy type class right at the bottom of our hierarchy, and that satisfies the requirement that every node except the root has to have a preferred parent. Something else we could do is move around which paths are preferred and non-preferred. So this is the diagram that shows how our paths were originally set up. So the red arrows show the paths that didn't commute, solid arrows are the preferred paths, and the dotted ones are the non-preferred. And here the two non-preferred paths were between ring and ADCOM group, and ADCOM group and ADCOM monoid. And if we swap these two dark arrows, so the one between ADCOM group and ADCOM monoid, and the one between ADCOM group and AD group, then this results in the path commuting. And in theory, you could probably do this to any graph, but for the size of the one inside MATLAB, it would take too long to do by hand. So if we were to do that, we would need a hierarchy builder style thing to do it automatically. The last thing you could do is you could take the arguments to module. So we were passing a semiring and an ADCOM monoid argument to module. And if we were to instead expand those to be the full set of data fields, which happen to be roots of the type class graph I showed in the very first slide with the very wide graph, then because they're all roots, the paths always commute because they always end in the same place. There's no intermediate node for them to get lost between. This isn't ideal though. It makes the term sizes much bigger, so the approval will be slower because we have these 6 type class arguments instead of 2, and all the 4 ones in blue will kind of have repeated terms inside them, so that's not very good. And it's not always possible. For the module case, it was okay because our proof fields only refer to the operators, but you could envisage a situation where the fields also refer to the proofs of those other type classes, and then we'd be stuck. Let's look at pack structures now. So is this all just a type class problem? We can create some pack structures by making a structure that contains a carrier type and then the unpacked version we had before. And we can do that for semiring and ADCOM monoid. We can then try and do this for modules, and the naive way to do this is just put the packed semiring in there, put the packed ADCOM monoid on there, and then say that the two carriers themselves form a module. And this doesn't work this is immune to our problem. It's not a dependent type anymore. Packed module takes no parameters, so there's no way for its type to not be equal to another copy of it. But it's also really hard to use because we've put the R inside the structure. And so if you want to state the type of linear maps between two R modules, you now need to add this awful inequality that the R modules are equal. Sorry, that the ring R is equal. And then you have to add this even more awful thing in the thing that says scalar multiplication moves across the function that does a typecast between one R and the other R. A better way of doing this is to move the packed semiring into an argument. So now when you're talking about linear maps between two modules over the same ring, then this is just enforced by the type system. And so now there's no cast on the two fun, and there's no equality. Unfortunately, by moving this from a field to an argument, we have made the same problem reappear that we were trying to avoid. So now we have this eta problem for the R argument. This time, instead of between a ring and encode monoid, we're getting it between packed commutative rings and packed semi-rings, where you can either go via commutative semi-rings or you can go via rings, and you have the same problem. So to summarize, if you want to use this nested inheritance, then it's only really compatible with dependent types if you have eta reduction of structures. We can make this happen with canonical structures. It's not specific to type classes, and this seemingly hasn't been noticed before because everyone else has sidestepped it by accident. And the reason this all mattered is Lean 3 had been deprecated, Lean 4 was new, and the goal was to keep MATLAB alive by moving it to this new language, and this was a complete blocker for doing so for all the maths in MATLAB. The code samples on these slides that reproduce the problems are available at this GitHub URL. Thanks.